Vitis on the PinQZ2 board because the original reference code is for ZenQ7000. So if we want to use it on the PinQZ2, then we have to modify some setting on the board. And the last one is we're going to talk about the flow on the Z2. Okay, so here is the overview of the entire flow from hardware design to software design. So let me see. Okay, first you might have to use Vitis HLS to, I don't know, design your IP into a RTL package, right? And then you move on to, of course, you have to validate or anything, simulation, etc. And second, you will move on to Vivado to do the system design, which means is you use block diagram to build your entire system with your own IP and on-the-shelf IP. Okay, and after you've done that, you will get a platform information from Vivado, and we can move on to the Vitis, which you can write your software application on your own hardware platform. Okay. So because I have a ZenQ PinQ-Z2 board, so I can test this lab on the Z2 board. And you should modify something. It's different from the lab 1 or lab 2. You have to, of course, you have to connect the USB onto your host PC. That's for sure. But you have to set the program setting here. It's a jumper to JTAG mode. Okay? And I suggest you set the power supply onto USB. Then you can do the next design. Okay? And I will talk about the entire flow. Oh, yeah, sorry. First step, as I said, you will use a Vitis HLS to design your IP, and you will do cosing and generate your IP. And step 3, you will do the system level design, which you use Vivado to build your system in block diagram. Yeah. And you can export your hardware platform information, which is XSA file. And you can read the XA file in the Vitis to development your application. Okay, then we know how is the entire flow now. Then we can start to do our lab 1, which is a simple Mac design. So first I will talk about how do you do HLS in Vitis HLS, and how do you do analyze in HLS, and how do you do a system design in this lab, and a little code analyze, and some option in the application. Okay, so as you can see, this, let's say IP is quite simple. You have a reset clear signal, and you do the MAC here, and send back the result. And well, when you doing this lab, you might not know this bundle means. It's if you don't mention this bundle, for example here, the default will bundle every signal into single bus. Okay, and the rest I think you guys all know. Okay, then I will demonstrate how to do analyze in Vitis HLS. So here, the original code you can see here. It's okay, and the critical path is under our constraint, so it's fine. And I don't know, there's nothing new here, but you can see here. You can see, let's see here. It didn't use any DSP here, right? It's 0. So I thought, why it didn't use any DSP if there is a MAC in DSP, right? So I do a little change in the reference code. I add the pragma, which is bind OP here, okay, to test if we can change the behavior of the tool, right? So I said, okay, first I change my code into a two-stage. I change the A multiply B into a one stage, and then add back to the register into next stage. So I can find the operation here, as you can see. And let's see the result here. First, the critical path is shorter than used to. And we really did use one DSP here. So it works. Okay, so that's, I don't know, the observation. And in the schematic viewer, I guess, here you can see it really used DSP for the multiply here. And the question is, why didn't the visitors use DSP for addition? And I guess the reason why is the addition is too simple. So it doesn't need to be used on the DSP. I guess so. Because I did define the addition and the multiplication here. Okay? And how do we do the system design in Vivado? Well, yeah.
You separate the multiplication and
Yeah.
look at your the variable with the DSP.
The implement is DSP, and the variable is DSP and the accumulate reg.
Yeah. So what I'm doing for adding one.
Yeah, because I don't know.
Separate the multiplication.
Yeah.
Adding.
You mean why? Because I don't know which pragma I should use for Mac. I cannot find it online, so I separate two stages.
Maybe you go back to the variable you put in the
Yeah.
yeah. So
But yeah.
accumulate rate.
Yeah.
So accumulate.
Mhm.
So 8.
Mhm. I mean, I don't know which operation I should fill because there.
No, it's not.
I mean the variable here.
Variable is
Add. I mean yeah.
The equation.
Yes.
The equation originally it's one statement, right?
Yeah, one line.
One line, right?
Yeah. It's equal A plus B.
Right. So the variable will be this one.
Yeah.
Okay, and then you specify this variable the bind up to DSP.
Yeah, and because I tried this with OP Mac,
right.
It doesn't work. So I think the Mac should be, I don't know, maybe some phrase, I don't know.
You may use let me find
yeah.
Yeah. So sign up you can choose
Here, I mean, there is no Mac. So, yeah. Because I did try Mac, but it doesn't work. And I used the insert directive with the GUI. and there is no Mac operation.
Okay.
So
Maybe
that's why.
Maybe you just don't use the app. I think that you would choose the.
Oh, you mean by resource?
Yeah. So.
Oh, okay.
Yeah.
You mean this one?
32-bit. Two bit.
Yeah.
Yeah.
Okay.
Right. Yeah. Go back to the statement.
Sure. Okay. Okay. And here is the block design of our lab one. And the one thing you should notice is usually we just push the automation button, right? And it doesn't work in this lab because we use interrupt here. So one thing you should be careful on this lab is in the default setting, it doesn't connect this line. So it will fail in the after application. And there is also, you should set the interrupt here, enable. And there is one problem my teammate encounter is, let's see. There is a bug in PinQ which related to the interrupt handling. So the workaround, I don't know, maybe it depends on the tool version because both of us, the tool version is different. So maybe that's why he encountered this bug, but I didn't. So the workaround is to add a handler here, this one. Okay, so the interrupt connect to here, and the IRQ connect to the ThinQ. That's our workaround. Okay.
So add the interrupt.
Yeah. Okay. Okay, then we can do the application code analyze now. So we can see here. First, we initialize the variable with the value assigned here. This area. Okay, and then we will initialize our IP here, which it will call this function. And basically, it just do some initialize and some check onto some status. Yeah, and if it works, then it will go through. Otherwise, it will exit here. And after we initialize our IP, okay, we ARM. So here is some ARM interrupt routine here with some handler and some ISR here. Okay. And after we all set it up, we can start to stream our variable into our IP, which is A, B, and clear. And one thing you should notice is here, the API call here is auto-generated by the tool. So in the reference code, the function name is changed. So how can you tell which function name you should use? Then you should check the here. In the VTIS, you can see here is your hardware platform right here, that one, okay? And you should check the hardware in the driver in your IP and will show up the API call. And in for example, this file, you can see the actual correct name you should use. Otherwise, you will just fail in this part. Okay. Then after you stream the data, then you can read the results here. See? But the first is you will should wait the IPs ready. And second, you can choose. Here is the fun part is you can choose either using interrupt or using non-interrupt driven test. So if you use, for example, you take one, you will execute this part, and you will use interrupt, and you will say uh, interrupt receive here, right? And if you choose not to use interrupt service, then you will have to pull in your function. And here you will say, okay, I detect it complete and the result here. And first we will get the hardware result, right? So we have to check with the golden result here. So we have a software Mac here to validate our design. Here is the software version. And then if it match, you will say match, and not you will say mismatch. Okay? Okay. So that's for the Mac part, and here goes my teammates.
You mentioned something this lab using the four,
I use ping Z2, and the reference code is using ZQ7000.
right? So,
Yeah.
So the whole configuration.
Yes.
So
Slightly different.
yeah. So what did you set up?
First, you set the jumper, right? After that, you have to export the XSA file. That's the key, because in the reference flow, it prepared the XA file for you. And for me, I generate my own XA file. Yes.
The XA file, download.
I created. You can, for example, I don't know, maybe here we have some. Sure. No? Okay. How do you export the hardware XA file here is you, first you design your system in Vivado, right? And in Vivado, after you generate the bit string, you click on the menu, there is export hardware, and it will export XA file, but notice that you should include your bitstring file in the XA file. Then you generate the XA file for this Vivado design. Then you can read the XA file in the Vitis. And you read in this hardware platform, then Vitis compiler knows how is your configuration. Then you can work with you can build your application on your hardware. Yeah. Okay. Okay. So let's wait. Mike.
So let's go to lab 2, FFT. In this lab, we do not create the FFT itself, but instead we create a front end and a back end, two IPs to accompany with them. The first will introduce how to do HLS in Vitis, and then we'll introduce all system design. The third will introduce how to do the application, and the last will analyze the code we write. In this lab, we create two kernel IPs. The first one is named real to X FFT. The second one is named XFFT to real. The XFFT is Xilinx FFT IP block. In both IPs, we use the Pragma HLS data flow to ensure that it can be accompanied with HLS string. And in both IPs, we have two for loops and then we can see in the front end, the first loop apply window function is the bottleneck and it utilizes the most resource on the kernel. And the for loops follows this order. We can see that when we apply the Pragma, HLS on row with a factor of 2, then the two multipliers are created, and then two consecutive read and write operations are present. Then the performance can be accelerated. Then we see in the backend, the second task, the scramble is the bottleneck. In this loop, we use the Pragma HLS pipeline but not rewind because in this algorithm we should use ping pong buffer here. We cannot start the next task before the previous task complete. So we can only use pipeline but not unwind here. This is all system design for the real FFT module. The middle one is the Xilinx FFT IP, which is built in, and the left one and the right one are the IPs we just created. In this hierarchy, we create four ports. The first one is the input, and then the output, and then the clock and reset signal here. The clock and reset signal are connected to all the three blocks. And then we can see the AP starter control signal of both the front end and the back end are connected to constant 1. And then some configuration data are connected to constant 0 of the Xilinx FFT IP. The hierarchy is created so we can use a real FFT submodule as in overall system design. The real FFT is instantialized here, and this is a link processing system. Remember, in Lab 2, we manually create two DNA IPs, one for read and one for write. But in this lab, we just connected, we put our cursor on the input port and then connected, draw a line to the SP0 directly. And then we draw the output to the SP0 directly. That means IP integrator will automatically create the other lines and then the rest of the blocks for us. So let's explain in detail what the direct memory access is. The CPU first will send an instruction to the DNA IP that you want to do data movement. So the DNA receives the source, the destination, and the width of the data, the length of the data. When it receives the three information, it can perform the data movement by itself, and then CPU can go on other tasks. When DNA finishes its task, it can optionally send an interrupt to the CPU. Then CPU can know that the DNA finished its job, but the interrupt is optionally, so we can disable it here. The Xilinx FTIP has three kinds of buses on it. The first one is the AXI light port. It's for control and configuration signal from the link PS to here. The GP port of the link PS is connected to the X-axis light. The second group is NXI, N2S, and S2NM. N2S stands for memory maps to string, and S2NM is vice versa. It's directly connected to the memory of the host, so it can, for N2S, it can read the data in, and for S2NN, it can write the data out. The third group is for peripheral devices. We can see that this NN2S port is master, and then this S2NN port is slave. Both ports are connected to all real FFT IP. We can see here the NN2S is connected to input, and then the S2NN is connected to the output. So that's how the Vivado, the Xilinx FFT IP, the Xilinx DNA IP works. And for this IP, it provided three modes. The one is the simple one, the direct register mode. And the second and the third one, we can see that in lab 2, we disable the scatter gather mode manually. So the second one and the third one are not used in this lab. So how to do application in Vitis was explained before. The .axxi file is a proprietary archive file which can optionally include the bit string, so we should split.
And first I want to clarify the Fifo segment on the interface and the IP stream. So first look at the this IP. So what's the interface generated from the AAHLS and how the source code I will move this.
For this one and this one are defined as
Yeah, so you have basically you have a three module, right?
right.
Yeah, you have three module, and that's the core. This is the host, so FFT is a stream interface.
Yes.
Okay, input and output. Okay, this module host that's the handling the input, right?
Right.
And so, okay, so this one that's the output, right, on the right side.
Yes.
Yeah, the output. And one is the interface. So it's a stream in the interface.
Of them are string.
String to memory.
Right.
This one is from the memory to string.
Yes.
Okay. And in your C code, what's the structure? So that's the code, right?
Yeah, that's the front end part.
This one is the front end part. Yeah, so let's look at it. I just want to make sure people understand. So the interface, in and out is one.
Right.
Or on the online. Yes.
Yeah. So this is the front end of the code part. The data in and out both are string, right?
Yeah.
Yeah, both are string. And this one is so that's the top, right? Yeah.
That's a backend.
That's backend IP.
Yes.
So it's also data flow, and that's only accepted to real.
Because the real FFT is done in the Xilinx IP, in the on-the-shelf IP, not created by us.
Oh, that's important. Okay.
So
Yeah,
the
yeah.
three module, we only create the front end and the back end. The core is on the shelf.
Oh, okay, okay. So that's the key for this lab.
Yeah.
Yeah. So it's often that you design an HLS IP.
Yeah.
However, you need to integrate some other RTL modules, especially the bus interfaces. Yeah. So can you explain more detail about the flow? Okay. For HLS part, you go to the VT's HLS. Okay. And then you take out the RTL parts from the library. Yeah. And how do you integrate them? And how do you validate? Yeah. I think that that's the key for this lab.
Okay.
Yeah. And that's a real situation. Yeah. Often you use some IP from Xilinx library. Yeah. Okay. So can you address more about this flow? Yeah.
The motivation of creating the two IPs are less if we process for complex data of the waveform, it will be
In the C code, you don't integrate the RTL part. RTL part is only integrated in the block design.
yeah.
Okay. Mhm.
So the two IPs are created in VT's HLS, but we integrate them in Vivado as a system design. We instantiate the two blocks along with the built-in the next FFT IP, which is on the shelf. So in the last, we give a brief analysis about our code host program. In the beginning, it's quite similar to the left one. In this initialization, we look out for the configuration and then initialize them. But we should notice that we manually disable the interrupts of the DNA IPs because we don't need them. We just wait the kernel to finish its computation. So when we successfully initialize the host program, we generate the waveform on the host side. Is to generate a sinusoidal wave here. Then we flush the cache. We flush the cache from the data cache to memory before we do the data movement. This is important because if we do not flush the data cache, we may copy invalid data to the kernel. So when we flush the cache, we can do a simple transfer from DNA to device. Yeah. For this approach, we
this data that actually will interact with the accelerator. And the data from the beginning is saved in the non-cache memory. That will be saved. So it doesn't teach how to use it now.
No, because this map actually is to tell you how to go through entire flow instead of the.
So you find out this interesting thing.
Yeah.
yeah.
So I just mentioned that that's a very common issue that we will encounter. So for this case, I would suggest that normally for a position, you communicate you don't actually, for those data, you have to distinguish two information. One is the control status, and one is the data. Data is a lot of data. Okay, so for the host program, they don't normally process the whole data, but they do need to look at the status of the control unit. Yeah. And so normally, what we would do is for the data, we save it in a non-faithful region. So you don't need to have the overhead to flash that. And so we only put the control of status into the faithful region. So for this kind of design, the status that okay, for the kernel. Actually, for the status, you can read the I/O device to read the process. But the I/O actually is too slow. Okay, so what we will do is using the sending the message. That means the control, the accelerator using the master cycle only drive the status signal to the memory. And that memory will be cacheable. So that the process can immediately read the status. So it's fast. Okay, instead of to have a process using the memory map IO, that's slow. It's read action. And for this action, then you actually read the memory, either read from the system memory or faster read from the cache. It's very fast, one cycle. Instead of spending hundreds of cycles to read from the IO. And for the data, as I said, we remove this from the processor core.
Oh, okay. Okay. Remember that when you move the code to the accelerator, you move the address space to separate I/O device address space. There are a lot of overhead involved. So you have to pay attention to all the information you communicate and leverage on the system features, architectural features, to minimize all of the communication overhead. Yeah, so what I just said is one way to optimize the system. Yeah.
And then we go on 8 test cases. The first will copy the result back from the device to DNA. We can notice that the two functions are the same, but the last argument is different. So then in this while loop, we wait for the DNA IP to be not busy. This is for the blocking. And then because all spectrum data is saved in the local variable which is cacheable, we should invalidate the data cache to get the correct result when we evaluate the data in this loop. So if the DNA IP is not busy, we can send the next input to the IP from DNA to device, and then we just print some message for validation. Thanks for your listening.
And so I think it is that how to
With the RTL libraries, yeah, and that's so in the future project you will encounter most of the cases like this one, yeah, and also it's good that this team present you flush the cache. Yeah, yeah. So the cache coherence in the system is also a critical issue. Yeah. Okay, it's good. Yeah. So we start.
So next one, or do we take a break? Or not?
Oh, you haven't finished?
I have the last.
Oh, really?
Yeah.
You only present half of your presentation.
No. Lab B is the.
Oh, that
Is the first one.
Oh, that's the left. Okay. Oh, okay. Good. So maybe after you finish, what time is it?
It's 10.
It's 10. Yeah, probably you finish.
Maybe this one. Where is the? Oh yeah, this. No, not this one. I guess this one. No. Or maybe in this. Yeah. Why?
It's not here.
Yeah, it's not here. I did upload in assignment. Do we need to upload into the OneDrive?
Oh.
But I didn't receive the message to upload it.
So then maybe next thing you go upload.
Okay. Or maybe I upload it now. Okay. Yeah, 就表示这样带了。哦，好。Okay, good morning everyone. My name is Hai Yilin, and today I'm going to talk about data flow debug and optimization, and this is the topic of Lab B. Okay, so this lab contains two labs, which the first lab is data flow viewer and the basics. Okay, so here's the source code of the lab one, and you can see the top function is the diamond, and there's four sub functions, which are lab function A, B, C, and D. And actually, because we're talking about data flow, so we only care about the data dependency. And you can see that the input here is that in, and the function A generates two outputs, which are C1 and C2. And C1 is the input of function B, and C2 is the the input of function C. Also, function D takes the input of C3 and C4, which are the outputs of function B and function C. So we can see that function B and C depends on function A, and function D depends on both function B and function C. Okay, so here's some function, the source code of each function, but you can see they are all basic operations, arithmetic operations, and they're not important. So I'm just showing that actually the content in the function are not important. So we'll just go through the data flow graph. And this is the data flow graph after the C synthesis. And you can see they'll show the data dependency right over here. And first of all, the ports will be shown in the gray horizontal bars, which is here and here. They are the ports of all the functions. The function diamond, which is the top function. Also, the blue boxes here, these four blue boxes shows the subfunction or the loops, but we don't have loop here, so it means subfunctions in the top function. Also, the blue edges which is here and here and here, they represent the data dependencies between the function. And lastly, the gold edges, which is here, they are the inferred FIFO or PIFO channels. And now the II and latency is not yet available because we only done the C synthesis, and those indication, which is II and latency, will only be shown after the co-simulation. And here's the data flow plan continue. This is the data flow plan after the co-simulation, and you can see that because the data flow optimization is a dynamic optimization, so it can be only shown after the co-simulation. Also, you can see the dependency here. Indeed, function B and C is not dependent on each other because they don't have the input and output dependency. So after the function A is executed, function B and C can be executed in parallel. And after function B and C are both done, then we execute function D. So the conjecture in the last 5 slides is proved. Now we can look into the data flow table. And first of all, I would like to introduce the co-sim stalling. This index shows the percentage of the simulation time when the old process is stalled. And then this is the co-sim read block and co-sim write block time. They are the time that the block read or writes the channel. Then there are the co-sim no start and co-sim no continue. They are the time which represent the forward and the backward back pressure. And so the next one, I'm gonna introduce the forward and
So we
yes.
don't want to see there is a so
No, because it will lower the performance.
we don't.
Yeah, it will be better that if it's 0.
How about the previous previous slide?
Okay.
The cosine read time, the cosine write
Uh-huh.
we also don't want to see.
No, we don't want to spend time on all of them. Okay, so you can see the actually we have the 0.76% in the left side. So I'm gonna talk about the result of that, the reason of the 0.76%, and they are resulted from the actually only backward pressure because no start is 0, so only no backward pressure, which is related to no continue. Okay, so forward pressure means that the execution stops because the consumer cannot take the data from the producer because the producer is still generating the data, so the consumer cannot fetch the data from the producer. So it causes the forward pressure. And the back pressure means that when the producer is done generating the data and the consumer is still processing the data, so the consumer is not capable of taking the data from the producer. So let's call the producer to stall to wait for the consumer to finish the process. And they both indicate the problems that may lower your performance because your design is stalled, then it takes longer to finish the whole process. Also, if the situation gets worse, it may cause a deadlock because if the producer wants to give a consumer data, but the consumer is also waiting for another producer to finish the data, and they both cannot read or write the data from each other, and they will cause a deadlock. So in this lab, we have the problem of back pressure because you can see there is no continue in the left side. Okay, so to further investigate the waveform when we open the Vivado simulator and the waveform viewer, and you can see that the function is called 3 times, and the function A starts first because yes.
Can you give us that one? on the data flow. First, all the text interface using Fifo.
Oh, they use Pipo because it is a default form of the
So
data.
it's using Fifo. So
I think it's Pipo. Yeah, in this level. Yeah, it's Pipo. Yeah, I said Pipo. Pipo.
Oh, okay.
Mhm. Yeah, Pipo is a default form of the data too. Yeah, it's ping pong. Yeah.
That's very important.
Yeah.
Okay, if we change Fifo,
No, because
there will be no preference.
yeah, because you can just start once the data is written into the file. But if you use ping pong Pipo, then you have to wait the producer to done all the process, then the consumer can start. Yes, because it's ping
But
pong.
still cannot eliminate the.
No, we cannot. Hmm. Okay.
So, would you explain more why, even though I use buffer, still have a penalty? Not much, only 0.
Oh, right. Oh, crap. I forgot. Okay, I'm supposed to talk about that. But okay, so here you can see a latency. The latency is 51, 52. Oh, actually, the I is more important. So average is 50, but here is 51, 51, and here is 52. So you can see the consumer needs more time to done all the process. But when the consumer is still processing, the producer has done all the process. So it causes a stall because consumer hasn't done yet, but the producer is done.
The rate is the same.
The rate?
The rate. Throughput rate.
Oh, yeah. Yeah,
The throughput rate is the same.
actually,
The latency is
yeah, actually, I hear you can is also longer because averagely this is I also the consumer is has a longer I here and here and this is the
longer.
mm-hmm.
If it's longer and the first task will always stop.
Yeah. Mm.
I told the the throughput rate is the same because
Yeah, it's supposed to be this. Otherwise, the producer cannot start again. Yeah, but the data here, yeah, but the data here is not consistent. Oh, I is.
I believe that I still want. Yeah. All of the throughput rate.
Oh, yeah. Okay.
Otherwise,
Yeah, it doesn't make sense because they are dependent. Mm-hmm. Okay. Okay, so function is called three times, and function starts first, of course, because all function depends on function A, and then function B and C are not dependent on each other, so they can start simultaneously. And after function B and C are done, then function D starts here. So you can do first cycle, second cycle, and the third cycle. Also, this function is executed in pipeline, so you can see here they overlap. And the red ellipse, oh, it's not clear now. They are red ellipse. I use a red ellipse to indicate when the function is stalled. Okay, so we further look into the waveform viewer. And here you can see the stall continue is asserted for a short time. This is because, oh, okay. Yeah, it's a glitch right over here. And this is because when the function A is done, function B and C is not yet done. So the function A has the stall not continue. Here, to indicate function A to stall for a while to wait for function B and C finish. And you can see here function B and C also have the stall no continue. This is because function D takes more time to process all the data. So when the function B and C are done, function D is not yet done, so it has to wait for a while to wait for the function D to finish all the data. Okay, so we can conclude that we have the back pressure from function D, which calls function B and C stall. Also, we have the function back pressure from function B and C, which calls function A stall. Okay, and now I'm gonna talk about Fifo, which is used in this lab. This is a default form of data Fifo, and when we use the Fifo, the consumer can be executed only after the producer is done. So in this case, function B and C has to wait until the process of function A is done. And Fifo is used when the data is written into the Fifo randomly. So in this case, we cannot use Fifo because a Fifo needs to the data generated has to have the same sequence that the data is consumed. Okay, so I'm going to talk about Fifo. If in our lab function B and C consume the data in the same order that the data in function A is generated, then we can use Fifo. And if we use the Fifo, then the function B can take the data once after the function A has generated this data. So it doesn't have to wait function A to finish all the process. And in this way, we can avoid the stall because function B can soon be asserted once function A finished generating only a part of data instead of the whole part of the data. Okay. Okay, so here's the second lab. The second lab, the topic is Fifo sizing at deadlocks. And this is the source code. And in this lab, we examine two cases. The first function is proc1 and proc2. And the first case is proc1. And in this case, we have two subfunctions, which are proc11 and proc12. And proc11 is the producer and proc12 is the consumer. And proc11, which is the producer, writes into a Fifo for 10 times, which is right over here. You can see there are a for loop for 10 times. And the proc12 is the consumer, which reads the data channel 1 and 2 and 1 and 2 alternatively. So proc12 here, you can see they read the data channel 1 and 2 alternatively. So in this case, we need the depth of a Fifo for 10. The size has to be 10. Because if it is not 10, then when proc11 writes the data, okay, so this is channel 1 and channel 2. If the proc1 writes data to the channel 1 for 2 times, then the data channel 2 will read the data first from data channel 1. Read the data first. And then the proc12 will start to try to read the data from data channel 2. But there's no data right over here because proc1 still wants to write to the data channel 1, but the data channel 1 is full, and it cannot write to the data channel 2 before it is done writing into the data channel 1. So proc11 is stalled because the data channel 1 is full. But proc12 is also stalled because there is no data in the data channel 2. So it causes a deadlock because both the consumer and the producer cannot continue. Okay, so here's the second case. the functionality is the same. However, it reads the data and writes the data in different order. You can see here, proc11 reads and writes the data, proc11, sorry, proc21. Now it's proc21. Okay, so here, the same. The proc21 is the producer, and proc22 is the consumer. And you can see proc21 writes to the data in the same order. I'm sorry, write to the data alternatively, which is data channel 1 and 2 and 1 and 2. And proc22, the same. It reads the data from data channel 2 and 1 alternatively. So in this case, we only need the depth of 1 because once data channel suppose it is 1 and 2, and once data is written to data channel 1, then it will return to data channel 2. So when the proc22 wants to read the data, it fetch here, and the data channel 1, the data in the data channel 1 will be released, so it will be empty again. So the proc21 can write into the data channel 1 again. So whenever data proc22 fetch the data, it will leave the space for the data proc21 to write again in the data channel. So only the depth of 1 is required. And this is the data flow after the code simulation. Oh, in this slide, the source code will cause the deadlocks. And the purpose of this lab is to fix the deadlock. So you can see after the code simulation, there's the deadlock right over here, and the function, which is highlighted in the red, means that there are deadlock. And the fault channel will be highlighted in the red arrow, and the empty channel will be highlighted in the white arrow. Okay, so we can further look into the data, the Fifo table. And those Fifo which are full or empty here will be highlighted in red. So you can see here it is full, but here this is empty. Also, there are 3 ways for us to fix this problem, which are manual Fifo sizing, global Fifo sizing, and automated Fifo sizing. So first of all, I'm gonna talk about manual Fifo sizing. This is the user responsibility to modify the depth. So here we modify here to 10. All of them, we modify them to 10. And here, because you can see this is green now, it means we pass the test and there's no deadlock anymore. And more importantly, you can see here, the data table will report the maximum depth during all the code simulation. Which one? Yeah, one. Yeah. On some of them only requires 1, and some of them requires 10. Okay. So also you can see, as I told you, the data channel 1 in the first process needs 10, but in the second case it only needs 1. So, oh sorry, not this case. This is also proc1. So, okay, never mind. So yeah, it is 10, and so we also need depth of 10 to pass all the tests. But you can see some of the Fifo doesn't need 10. So if we specify 10, it kind of wastes the resources. So we can remodify this Fifo depth to 1 to save the resources. So if you want to use the manual Fifo sizing, I would suggest you first modify all the depth to a large number to ensure that you'll pass the test first. Then you can check the cosim max depth right over here. It will tell you the maximal depth happened in in the code simulation, then you can just modify the depth to the code sim depth. Then you can pass the test. Also, you can save the resources. And the second one is a global FIFO sizing. And after the C simulation, the console will tell you the suggested FIFO depth right over here. And you can modify the FIFO depth to 40. In this case, in this lab is 40. And once you modify the depth of 40, then it can be ensured that you'll pass the test in code simulation. And after that, you can just check the cosim max depth for each FIFO, and you can just modify the depth to the cosim max depth to save the resources. And the last one is automated FIFO sizing. In this FIFO sizing, the Vitis tool will apply a heuristic algorithm. It will increase all the FIFO depth until the performance is no longer increased. So you can see in this step, it suggests to be 11 and 2. And once the automated FIFO sizing is done, you can also check the cosim depth and then modify the FIFO depth to the suggested cosim depth. And also because it's a heuristic algorithm, so it doesn't guarantee that the FIFO depth that this tool finds will be the optimal case. So you also need to check it out to the cosim depth and modify it manually. But it will ensure that the suggested depth, you can pass the co-simulation with the suggested depth. Also, so here's a summary. And data flow is a very useful table which shows the topology of all the data flow. And it is very useful to detect the problems such as the deadlock and the poor throughput performance. And also, you can track the maximal depth after the co-simulation. And you can also change the FIFO depth to the cosim max depth to save the resources and also pass the test. And it also detects the deadlock for you. For example, we can see in the last slide, the process with the deadlock are highlighted in the red, and it also highlights the FIFO that are full or empty. So it can help you to narrow down the cause of the deadlock. You can just look into the full and empty FIFO, and you'll know that, oh, they may not be, the size of the FIFO may not be enough. Then you can resize the FIFO, then you can fix the deadlock. Also, the data flow table also provides you the time the process is stalling. So you can check in which parts this process is stalling, and you can check whether there's a forward or back pressure, and you can refactor the designs, then your performance will also increase. So it helps you to manage the size of the data channel. It helps you to resize the FIFO to increase your performance. And this is very useful for a data flow table. Okay, so that's all for today, and thanks for listening.
I think that this lab will provide very using data flow.
Yeah.
Things that could get very complicated because the topology of the data flow. In the example you show, you have a form and join.
Yes.
Yeah. And sometimes it has a feedback. I think it get more complicated if the latency is very
large.
Yeah, the latency and the throughput rate is very good.
Mm-hmm.
And this level simply gives you a framework that how to analyze it. Very simple example.
Yes, it's a very simple one. Just show you how to operate all the data flow table. Yeah. Okay, thank you. it is. Okay, then this is my lab B, and I'm going to talk about balloon filter. Here's my agenda. First, I will talk about what is a balloon filter and where can I use it in the application. And second, I will do a little code analyze on how do we do the hash function and how is the loop for the hash function and how do we compute the overall score and the overall design view. And the third part is going to talk about performance evaluation. I will talk, there is one issue on this reference code and how is the actually function speed up and some utilization and resource something, and one optimized way. Okay, let's start. So what is a balloon filter? The balloon filter is that it uses a hash table based data structure that determines when an element is present in a document, and later we will see an example. Okay, and in this technique, false positive is possible, but false negative match are not, which means is if you send a query and it will either return possibly in the set or definitely not in the set. So we can use this technique for the first pass document filtering, okay? Because the way it is. Okay, so here we can see it's a balloon filter example. For example, my document is a set contain X and Y and Z, and we can compute its hash table here. For example, I guess it's 18 bits, I guess. Yeah, and after we compute this document into a, let's say, hash table in this 1-bit array, 18 bits here, and we send a query on word W, and we compute its, let's say, hash into this table, and we compare to this document here, and we can see there is a 0 here, which means is this element W is definitely not in the set. Okay, so then what is the scenario if it's a false positive? For example, this is the original document here, and sorry, this is misbit. And if we query element K, and turns out it's this 3 index, then we will thought, hey, maybe it is in the document, but actually it is not. So this is a false positive example, okay? Then where can I use it? I think it mostly used in the nowadays non-SQL database. For example, this Cassandra, maybe some of you might use it. It's a non-SQL database, and you can use this technique for the first pass document filtering. And also you can do some, I don't know, disk query something. Okay? So now I'm going to talk about code analyze. First, how to do the hash function, which is important. Okay? So here we can see this is our function name, and we will get a key and a seed. And this is a, let's say, we will first initialize the hash with the random value. Okay. And then we will mix the 4 bytes, which is 32 bits in this lab at a time into the hash. And we will do this computation here. Okay. And if we want to do, let's say, 32 bits here, first, let's see. Here's one loop here. It's called a number of document, which means is the total document you input into this application. And in each document, we will compute the input document input document words. For example, in this lab, we use 32 bits Bloom filter. So we will compute the hash 32 times for one document, for example. And we will do the, you can see here, the key point is we use this function, hash function twice in single hash bit here, okay? So here you can see well, you can see if we unroll this part, for example, and we can easily achieve the parallelism, which I will mention later, is how much copy you want to copy this hardware, and you can accelerate your application. And of course, there is a top speed, let's say a limit of this speed up, and we'll discuss it later. And after we compute every document with every hash, right? So we will get, let's say, one document and 32 words. And in each word, we query, let's say we read it and compute the word into a entry and take the entry into a word ID. And we can query the word ID with the frequency and can compute this single score, and we do the summation of each word, which means it's single score, into this document total score. Okay, so for example, I will have let's say document 1 and 5 points, document 2 7 points, and maybe document 3 80 points, and I would select this, for example. So since we already saw the two main functions, so here is the overall design view. First, we will transfer our document, which is input, to FPGA memory. And then we will start to do the hash function, and we will get each word, right? And then we send the array back to the host. And the host will do the summation of the score here. So the overall execution will be like this graph. Okay? So far, so good. 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 Okay. Then we can start to do the performance evaluation, right? Okay, here is the first issue I encountered, is if you just run the reference code, you will encounter the bad allocation. Why? Because the reference code is running on U200, which that FPGA use DDR as its onboard memory. And in our case, we use U50, right? And U50 use HBM memory, which is high bandwidth memory. And the special of high bandwidth memory is you can get a very large bandwidth, which means one word is very large, but the depth is, let's say, shallower than DDR. Okay? So if you allocate, for example, here, this one is a document number. For example, this case, 15,700, etc. It will, you cannot allocate in a single pseudo bank in high bandwidth memory because let's say DDR0, this means the first bank. The default is 16 gigabytes. And in our case, HBM is only 256 megabytes. So if you allocate more than this specific document number, you cannot allocate the memory on the FPGA. Then you will get the segment fault here. Okay. So that's it. So for example, yeah.
Segmentation doing the hardware.
Yes. Yes. Yeah. You can see. Okay, then in the previous code, in the execution timeline, it will look like this. First, we write the document, right? Okay, we write document here, and then we compute the hash here. And after compute, we send back the flag array back to host and make the host compute the score. Why we want to make CPU to compute the score? Because the tutorial said if you doing it on the FPGA, it doesn't gain anything. So it just send it back to the host. Okay, so as I said, here is pure CPU execution here. For example, I use this number. Yeah. Yes. Eventually. Yes. Yeah. Okay. So here is a purely CPU execution, and you can see the total execution time here is around 266 milliseconds. And it divides into two parts. First one is hash part, which we will accelerate in FPGA. And the compute score is almost time constant in this lab because it always computes on the CPU. Okay? And here is only one parallel function, which, what do I mean one parallel function, which means is first we send the data, let's say data is here, and we have to compute the hash, right? So let's say hash here, which means, let's say write back. That means it's only one parallel function. And if we make two, that will be PF equal 2. And in this case, it's 1 here. Okay? So you can see the total execution time is almost the same. Almost. Right? Later I will have a chart. And if we double the hash function, it will speed up. So there's 4 times. Then we can see this chart. Okay, for the only parallel function equal 1, we only gain almost nothing. It's normalized to the CPU runtime. And if we parallel 2 times hardware, we'll almost achieve 2 times, etc. And you can see here, if I 8 times the hardware resource or 16 times hardware resource, the gain of speed up is almost the same. Which means is, if you, it's a resource constraint situation. So in this situation, you might not want to use 16 parallel optimize because I will discuss it later. Yes. So yeah. So you can see here the hardware resource is almost twice, but the speed up is nothing but 0.1, etc. Right? So we agree this one is the optimal solution. And you can see here is PF equal 1 application timeline. You can see first we set the data and FPGA will run the hash and then you will write out the data. So what if we say 16 parallel function? So you can see the data transfer time is almost the same, but the total execution time is much faster. But yeah, there's nothing new here. So how can we achieve better, let's say, performance? So you can first observe the execution timeline here. We write this huge document, right? And then we said, okay, you go compute the hash. And that's not efficient, not really. So what if, let's say, what if we create 2 split buffer here? First, we write the upper half document, and we told the FPGA, okay, go compute this upper half document. So it starts, and then in the meantime, I write the left half document here, right? So then after it computes the hash, and I can start to compute the lower half. So it will, let's say, a little like, I don't know, pipeline-like execution timeline here. Also, the read, which means transfer the data, the flag, back to CPU's host side, is split into 2 parts to overlap this time. So in theory, it can achieve better performance, right? And yes, it did. For example, here the upper 2 legend is with 1 buffer, and the lower part is 2 split buffer. And you can see in the lower parallel function, I think it because it's let's say compute bound situation. So if you gain your overall, let's say, efficiency on the data transfer, it doesn't really gain a lot. You can see it's almost the same. But you can see after, let's say, 8 or 4, the performance gain is huge. Let's say this one to this one, this one to this one, right? So we did speed up overall, but the same situation here is it still encountered. It doesn't really need to be parallel as 16, let's say, function parallel. I think if you keep double the buffer, then you can see the scale is going to be, let's say, more. Okay? Then that's my presentation. Yeah.
We use
Yeah.
I still doubt. So you were saying compute store will move to the PTA.
Yeah. In tutorial, it said it doesn't need to. Yeah, I can try.
Yeah, we imagine.
Uh, mm, I guess because the overall computation is, let's say, do increment, let's say, partial sum until
The compute basically is the histogram.
yes, yes.
Yeah. So when the compute done in the data combine with
Uh, maybe, I guess, because if this is like a histogram, like, right? The another approach you might use a hash-based histogram algorithm. Then it will maybe we can speed up this compute.
But first, try to figure out what is the whole way to compute
Yeah.
and figure out why from that part move to the PTA.
Sure.
That's one I think. That's one thing. Another thing is whether the compute integrate
Mm-hmm. Okay. So that's my presentation. Any question? No? Okay. Thank you.
okay, so
Okay.
Oh, okay. OK，
哎，你不用塞到耳朵里面。
就这样子。
部分是在这节目。
OK，好，谢谢。Okay, so my topic today is bottom-up RTL kernel construction. So I'll first introduce about this tutorial. So in this tutorial, we will generate a fittest compliant RTL kernel from an existing RTL design. Then we will perform host programming for the RTL kernel with XRT native API. And we'll use fittest hardware emulation to get an inside look of the RTL kernel operation. So first, we'll introduce our RTL design. So our RTL design implements the AES encryption algorithm. So it is a commonly used symmetric key encryption algorithm. So before we perform the encryption and decryption operation, an operation called key expansion must be run when a key is given. And in AES, we have 5 widely used usage models. So in this design, we only consider 2 of them, which is ECB and CBC. So we can see the AES ECB encryption decryption operation. So in the ECB mode, the encryption decryption run quite standard. And in the CBC mode, the encryption of the next stage will be affected by the ciphertext of the last stage. Then we will see the block diagram of this design. So this is a simple AES accelerator design that comprises 2 kernels, which is kernel AES and kernel CBC. So the kernel AES is the AES computation core with AXI stream slave and master port. And kernel CBC handles the host kernel data exchange and the implementation of AES ECB and AES CBD modes along with kernel AES. So we will start by introducing the kernel AES. So this is the block diagram of kernel AES. So this kernel includes 4 AES modules, each of which are connected outside with AXI stream slave and master port. So there is also an AXI slave port for kernel control, which is the here, AXI control slave. So in this design, we use 2 clocks, and one for external AXI port and the other for internal AXI port and AES core. So in this way, we can speed up the AES design with faster clock. And we have to use a clock converter to convert the clock between the external AXI port and internal AXI port. So we will first take a look at the RTL IP in this design. So in the RTL IP, we specify the AXI interface as input-output signal in so wait. Okay. So in the RTL IP, we specify the AXI interfaces and as input-output signals in RTL. And later on, we will use Vivado package to generate the IP and pack the design together. And then we handle the connection between IP in RTL2. So we can see that we connect the 2 clock with
the clock converter here. So one with the slave and one with the master clock, and also connect the AXI string interface together. So we will, in this stage, we will introduce the, so we will introduce the block level protocols in this stage. So, okay. So this kernel is the mixing of AP control num and AP control HS block level protocols. So the AP control HS is used for the AES key expansion operation. So we mentioned before that we must run a key expansion algorithm before we perform AES encryption and decryption. So this means that the host will start and wait for the finish of AES key expansion first. And AP control num is used for general AES encryption and decryption operation. So this means that as soon as the kernel receives input data from AXI stream slave port, it will start the operation of automatically and send the output to AXI stream master port. So then we will proceed to generate the essential IP in this design. So we can see that from the block diagram before, we use several IP in this design. So the IP uses in this design is listed below. So we can generate this IP first in the Vivado Tcl script. So after we generate the IP, we can proceed to pack the design together. So in the first stage, we will create the Vivado project and add the sources into the project. So in this stage, we will see that first, we create a project called kernel AES. And then we add the source file, including the RTL code, which is the kernel AES.sv and other essential RTL implementation. Also, we added the generated IP design from last stage. So after we create the project and added the essential design sources, we can proceed to infer the clock, reset, and AXI interface and associate them with clock. So in this stage, we first infer the AP clock as our interface clock and the reset signal. And then we will associate the AXI interface with our clock.
So this is the default.
Yes. Yes. Yeah. To pack the RTL design and. You mean the IPX? I think it is. So this Tcl script is given in this tutorial. So I think IPX is the interface of the namespace, kind of the namespace of the command. So the infer bus interface is under the IPX namespace.
So you can integrate the design without using the GUI.
Yes, this tutorial mainly use all Tcl script based. So they didn't use any GUI interface. But you can also use the GUI too, yes. But in this design, we use Tcl script base. Okay, so I will continue. So after this stage, okay. So the step 3 is we have to set the definition of AXI control state including the control signal and our kernel argument. So, you can see that we add a register to our AXI control slave, and this register corresponds to our argument in RTO design. So this is very essential because we have to, when we perform host programming, we have to change the argument in the design by using the AXI control slave. So we add the register for each argument and then set the description and the offset and the size of it. Okay, so in the last step, we package the IP and generate the BTS kernel file by several commands. And then we have generate the XO file for this kernel. So after this, we will proceed to generate the XCL bin file, and for the hardware for running in the hardware or hardware emulation later. So since we haven't implemented the kernel DBC yet, so we have to first generate the AXI string master and AXI string slave to provide and receive data from kernel AES. So we write a simple memory map AXI to AXI string kernel and AXI string to AXI memory map kernel with high-level C language. So this two simple kernel is named as strm issue and strm dump. So strm issue provides the data into string master, and so kernel AES will receive the data from strm issue. And after kernel AES finish the encryption or decryption operation, strm dump will receive the data from the AXI string master. So in this stage, because we will proceed to link the design together. So in this stage, we will show how can we use FITIS compiler and the FITIS linking option to link the design together. So this is the FITIS linking option file. The name is kernel AES test.cfg. So in this file, we can specify the connectivity of the design. So we can see that we connect the AXI string master in kernel AES to strm dump to the data input of strm dump. So it's essentially here. And because we have four AXI string master port, so we connect all of them together. And we also connect strm issue, the data output of strm issue to the AXI kernel, to the AXI string slave of kernel AES. So in this way, FITIS will know how to link the design together. So in the last stage, we introduce how we perform host programming. So we use XRT native C++ APIs to control the kernel execution in FPGA. So the host program generates random data as input, and then uses OpenSSL AES API to generate the reference server data. And when we execute the kernel, we use run.start function followed by run.wait function in a single-threaded way. So this is the common usage for AP control HS execution model. And when transition from encryption mode to decryption mode, we have to set a kernel argument mode to change the function of the kernel. So we will see some example here. So first, in this host programming code, we will first create the runner or instance. So the runner instance includes the key expansion operation and the strm issue and strm dump. So then we will proceed to set the kernel argument by using the setarg function. So we will set the kernel argument for each keyword and then proceed to run the AES key expansion algorithm. So AES key expansion is run as AP control HS. So we have to start the operation and wait for it to finish in the host programming. And then here is the example to write the data into buffer and run AES encryption. So here we write the data into the buffer named buffer strm issue. So we write the data into 4 of them, and then we just run we just start the running of strm issue and wait for it to finish. strm issue and strm dump. And because the kernel is running in the AP control none way, so it will automatically receive the data from the string, AXI string interface and proceed to, okay, so it will just receive the data and proceed to run the encryption algorithm in the kernel.
Using the DMA. Okay, here I'd like to mention something.
So remember that there is an overhead that between the host program and kernel, the coordination, synchronization. Okay, and for the data flow, we really like to see the synchronization done by data. Okay, so that the configuration, for example, configuration, this kernel function, currently the programming model is you go through the XI light to program the configuration address space, and then you come to the data phase, doing the data movement. Yeah. To tell the truth, it's not efficient. Okay, we really like to see a really efficient computing model is distributed data flow. Okay, so all the synchronization should be done in data phase. We use data to synchronize the host and the kernel function. That's the most efficient way, instead of going through a side channel to do the configuration. Yeah. So the idea, especially the host, there is a the configuration of the kernel function is a very small amount of data. So ideally, we really like to append the configuration in front of the data payload. Okay, and goes through the inline channel from host to kernel instead of going through a side channel. Yeah. So for CPU, so this is but for this scheme, it's a lack of something because you still need to program the DMA, right? Yeah. For this one, that the kernel function, the real kernel function is the stream interface. Okay, and then it has a stream issue and stream dump to do the data movement to the host. Okay, but for this model, it still has a DMA involved. Okay, so we really like to see something that the CPU can just write and followed by the data payload, and the kernel function just see the data available. And first you see the front of the payload is the configuration, then you start configuring the internal kernel, and then later on follow the data, like a network packet, right? Network packet comes in, there is a header. Okay, and then the network packet processing, just look at the header, then he knows how to process the rest of the payload. Okay, and we like to host do the same thing as with the kernel. Yeah, and this one, then you need to use a special kind of DMA called QDMA. Yeah, and this kind of programming model, I just see this year that Xilinx provide this programming model. Yeah, and it's using the QDMA. Yeah, so in the future, if there is a chance that that you may consider using a QDMA to implement this programming model, as I just mentioned.
Okay, so I will continue with the presentation. So next, we will see the implementation of kernel CBC design. So this is the block diagram of the other kernel CBC. So this kernel has AXI master interface to access input and output data in onboard global memory and to transmit and receive the data via AXI stream and master slave port. And this kernel will be connected with the kernel AES via AXI stream port in the Fitis linking stage. So we will see that in just a second. And this kernel handles the AES ECB and AES CBC modes. So also this kernel support AP control chain execution model. To see the implementation. The host program use multi-threaded run instance. So we will take a look just a second, but not in a very detailed manner. Okay. Okay. So we will also see the speed difference between AP control train and AP control HS later. So we will skip the packaging part because it is mostly the same as kernel AES. So we will just look at how we link this kernel with the AES kernel. So similarly, we use the Fitis linking configuration. This is because we run this tutorial in the command line interface, so we never use the GUI interface. So I guess if we use GUI interface like we use in lab 1 or 2, and we can manually connect them together using the GUI. But so okay, so but in this case we will have to specify the connectivity in the Fitis linking option file. And for the host programming, similarly, we generate random data and proceed to use the OpenSSL AES API to generate the cipher data. And in this case, both AES ECB and AES CBC modes are tested. So for the AP control chain execution model, the host program used multi-threaded techniques to simultaneously push multiple tasks to the kernel to the kernel. So in each subthread, a round.start function followed by a round.wait function is used. So we can actually simulate the AP control HS execution model by running this in a single threaded way, and we can compare the performance between AP control HS and AP control chain. So here is the comparison. So on the on this side, we are running in the single-threaded manner using AP control HS execution model. So we can see that the encryption test, the AES-ECB encryption test takes 22 milliseconds. And for the AP control chain execution model, we can see that the AES ECB encryption text only takes about 7 to 8 milliseconds. So it is quite a huge runtime difference in this case. So we come to a short conclusion that we introduced how to introduce a bottom-up Vitis-based RTL kernel construction. So given an RTL design, we can generate a Vitis kernel file and use them to integrate with other IP. So we also show that how we can use Vitis linking option files to configure the connectivity between RTL kernel and other HLS kernel. So in this way, we don't have to use the GUI, and we have full control to the connection between kernels. And we also show how we communicate with the integrated kernel with host programs by both AP control HS and AP control chain execution models.
So can you do me a favor? After class, you go check the host code.
Okay.
Okay, and find out how does do the yeah.
So remember in my class, I talk about the. Let me bring up the slide.
That's a should be the IO data flow, right? Let me bring up the PPT. Let's talk about wait. Should be IO. We're talking about the how to do the data flow. Wait. Okay. I could not find it. Okay. Basically, to do the pipeline, we split the programming into two parts. One is the input process. One is the output. Okay. For input process, as long as you see the AP ready, that means the kernel is ready to take next data. Then you can keep feeding the data. Okay. And then, so right now you have a multi-threading, right? Multi-threading. So there may be an issue there how to synchronize the thread. So because this is the only single kernel, or maybe there are 4 kernel, right? The AES, you have a 4.
We have
if it says full, then you have a full threading process. So each talk to one. Okay. Then there will be no interlocking. Okay. If you have if we want to, you have a full kernel, but you have only one interface, then you have a full thread. Okay, so the AP ready those signals, then you probably need semaphore to arbitrate for the resource. Then you feed the data. Okay, so that's the input process. Another is the output process. Output process, you monitor the AP continue. Okay, and then there is another. Then you feed the AP. What? Yeah. So basically, you split the communication into input process and output process. Yeah. So that's why I want you to look at the host code. How does it exactly communicate with this kernel? Yeah. And the result, please post in the discussion forum. Let everybody knows. Okay. Good. Thank you. Okay. So next one. Okay. Let's see. 好 ，OK， 哎，没有血了啊，血。OK。有可以，对，但是，
我不用删了。OK。Okay, so can anyone hear me? Okay, my lab is getting started with VT. This is the first tutorial of the series. So I think it will be simple and it will give a brief and good introduction for everyone, just what is VT and what is the basic VT flow we have to do. Okay, so here's my outline. In this lab, we have 5 steps. So first is I will give a brief introduction about the essential concept of a VT's FPGA acceleration flow. And then I will introduce how to install VT's tool, and because there are a lot of different software like VT's Vivado, VT's AAHLS, and I will give a short compare table about this tool. And then I will explain the source code of the example in this step. And in this step, just I think the purpose of the tutorial of this section is tell us how to write the correct host program, because we know we can write the HLS program, but what is the correct OpenCL program we have to write, and what is the step. And then there is some short introduction about how to compile. But I think in that 3, everyone do the compile stuff, so it will be easy for everyone. And then there is an overview of a VT's analyzer and show how to open the analysis report. Okay, so the essential concept of VT's application is we have 2 processors. One is like the CPU. It will be x86 or ARM processor. And it also needs a compiler for us to compile the host application. Also, we have an FPGA processor. And we can write RTL or HLS code. And also we need a course compiler for it. And we also have a debugging environment for us to debug the application we write in this flow. And then we will have some important performance profiler to help us to identify the bottleneck and help us to optimize the application. So this is a very simple and important picture for the whole system. So there are two parts. Left is CPU and right is right is an FPGA. So we can write some C or C++ application on the CPU, and we will write some HLS or RTL user kernel for FPGA. And they'll provide an API, is a Silent runtime API and some driver. If we follow the correct API, we can let these two to communicate with each other. And this is a build process. So for host application, we will have some G++ compiler to compile the C code to host executable code, executable file. So it's just like the C programming. So it's using G++ compiler. And for FPGA kernel, we will write HLS or RTL, and we will use a VTIS, their self-developed V++ compiler, and it will compile to the FPGA binary. And this FPGA binary will run on our FPGA board. So there is some build targets, and I think this is everyone familiar in that three. So first is we will do software emulation first, and then we will do hardware emulation. And the last step, we will really write the code onto the hardware. So what is the difference between software emulation and hardware emulation? I think just there is some text everyone can read or read after the presentation. But I think the key difference is hardware emulation. It will simulate the cycle and kind of the hardware detail or kernel activity for us. And software emulation, we can only check the answer is correct or not. But if we really want to test the result, we have to write on the hardware. Okay, so here in this tutorial, because there are lots of different type of FPGA, and most kind of application is run on embedded system or data center. And there is a slightly difference between these two FPGA building process. And if you are interested, you can check the tutorial for yourself. But I just give a quick introduction is, the first line is they tell these two kind of FPGA is used for embedding platform. And the U2000, U2050, this kind of series is used for data center. And there is only slightly different in the developed flow, but I think it's not really important in this tutorial. So here is some tool comparison between this kind of developer tool. So in Vivato, it's used for hardware engineer, and we use it to develop RTL kernel. And in VTIS is for embedding engineer. We can create some low-level firmware or some kind of boot sequence. I think the most important part is we use VTIS to integrate the software and the hardware. And for VTIS HLS, is for software engineer to develop hardware kernel. So we use OpenCL or Sky or HLS to develop the kernel. And there's another new tool. It's called VTIS AI. but I never tried it. But I see the distribution is used for data scientists to focus on develop AI kernel. Okay, so here later, so now I will show a simple example here and tell us how to we write the correct VTIS code. So this is a really simple vector add example. So the AAHLS here is on the left part. So it's really simple. You just add two vectors together. And the first thing we have to mention here is we have to, I'm not sure why, but the tutorial say we have to declare extern C to avoid the name mangling issue. But I think if we develop the VTIS AAHLS first, we don't have to do this. So I'm not sure if we don't do the extern C, what will happen here. Okay, so it's just a simple example. So after we write the AAHLS, and then we have to write the host program. Okay, so how can we write the host program on the CPU? So there are 4 steps, and then this is step 1. It's at first we have to initialize the OpenCL, and then we have to detect the silence device, and then we have to load the FPGA binary. And then we have to give some tools and kernel objects to let them to create. So here is the code. So we can see. Okay, at first we we define the binary file. And the binary file is the FPGA build target. So the AAHLS will build into this kind of binary file. And then we get the silence device. We have to detect how many silence devices we have. And then because there is only one device here, so we get the device on index 0. And then we create a context. And then we read a binary file into a file buffer. And then we load these two kind of things into the program. And the last step, we create a command queue for us, and we will do some step in later. So here's the first step, just how we can initial the OpenCL environment. Okay. So is there any question here? And I think the tutorial tells us it's just a very simple flow. And basically, every kind of host program, we can follow this kind of step to write our host program. And the step 2, after we initialize our OpenCL environment, and then we have to create the data buffer to help us to load the data. So first, we have to, in this example, because we have 3 arguments, 2 input and 1 output. So we create 3 buffer and needed to share data with the kernel. And then we have to map the buffer to the kernel argument. And the last step, we have to map both sides buffer memory to user space pointer. So here is the example code. So on the first 3 lines, we create 3 buffers. And then we set the argument. And then we map the whole site buffer memory to user space pointer. And the last part, we just randomly initialize the vector. Okay, so is there any question here? Okay, so if no, I will continue. And after we create the data buffer, and we have to execute the command we want to do here. So I'm not sure why the tutorial here says the kernel argument again.
But I think the main idea here is we have to schedule it. How can we transfer the input data into the device memory and execution, then execute kernel, and then we have to transfer the output back to the host memory. So here's the example code. So the example code here says the argument again. I'm not sure why, because the first 4 lines we do on this part too. But yes, because the set argument we do here. But when we run the kernel, we set the kernel argument again. I'm not sure why. But I think the main important here is the most important thing here is how can we schedule the transfer into how can we schedule the data transfer into the kernel memory. So the first line is we put the input buffer, and then we tell the kernel we have to transfer the code into the kernel. And then we execute the kernel function. And then we transfer the output data back to the host memory. So this is a simple concept. And then we call the finish to the kernel. Okay, so here's the example code. So if we do the following step, we can write a simple host program for the VT's flow. And basically every kind of application will follow this kind of flow. And after we write the code, we have to build and run. And this is same as the lab 3. So I think I don't have to take too much time to tell here. And after we build the code, we can see some report and analysis report. And there are 4 kinds of report we can see here. The first is system diagram and run guideline report and profile summary report and application timeline. So for system diagram, it's just a graphical view of the content of a Xilinx device. So it's just like the right-hand part. It will show the block diagram of each component and how it's connected to the ARM or x86 processor. And for the run guideline report, it will show some warning or suggestion for our application to improve the code. And for the profile summary, it will provide some detail for the whole application performance, like the hardware usage or some latency information. I'm not sure why there's not clear here, but you can see some maybe like lookup table. Oh, yeah. Okay. Yeah, so oops. But the app crashed.
You were saying Microsoft.
Yes, it is.
Here. What happened?
This one.
Oh, that would be.
Oh, yeah, okay.
So why? Oh.
Okay, thanks. Okay, let's continue. Yeah, so for the profile summary, we can see some like total execution time and some kind of information here. And there are lots of different tabs here. You can check some useful information if you need it. And for the last report, is the most important one, is application timeline. And in this report, you can see the time execution sequence here. And you can know more about how to optimize your code. So here's my presentation.
Timeline, you can get the timeline after synthesis
Yes.
and after processing.
After coding. Yeah, we only app gets from, yes, only after hardware emulation.
Yeah, okay. Power emulation, and you also can get the timeline for power. That means from the actual.
Yeah, I'm not sure, but I think yes.
So, yeah, we have, you can see three software emulation, hardware emulation, power,
Yeah.
timeline.
Uh-huh. Oh, I can see. Okay.
So remember, for power emulation, the data transfer, the code, the PCIe or etc.,
Uh-huh.
they are not accurate. Okay.
Uh-huh.
And also the memory, timeline, memory access, they
Uh-huh.
are using the map.
Uh-huh.
If you run in the power mode, then it's running the actual
Uh-huh.
and the process for the timing.
Okay. Okay. Okay.
Good morning, everyone. My name is Yang Zhongxian. I'm going to introduce the traveling salesperson problem. First, I'll introduce what this problem is, and then I will say the algorithm I use, and then I will show the CPU implementation, and then I will show the effort I pay on migration from VTIS HLS to VTIS IDE, and then I will show some optimization skills. I think all of you have heard of TSP before. There's a traveling salesperson. He wants to make a plan to visit through every vertex on this map. So he will plan I cannot draw something. Oh, wrong end. Okay, let's continue. So all of you have known this is an NP-hard problem, which means we can only find the optimal solution by looking up every possible solution. Well, there's some heuristic algorithm, but they usually gives only suboptimal solutions. Here's a possible path to iterate through every vertex exactly once, but not twice or above. So the algorithm should iterate through an index I from Lilo to factorial of the n-1 and n-1. We can generate a permutation by this algorithm. This algorithm, the first step is to take the I as the input and then generate the so-called lemma code. This is to generate permutation in graphical order. And then the Lilo will generate this order, Lilo 1, 2, 3. And then the tree will generate the order Lilo 2, 3, 1. When the lemma code is generated, which takes a linear of time complexity, we should decode this permutation to to transform the number code to the permutation vector. When the permutation vector is generated, we should also prepare the distance table on host program. We should compute for every two nodes. There's a distance between them. The Euclidean distance between every two nodes are pre-computed and saved into a table. So the floating point numbers are scaled to unsigned short integers. We should find the minimal possible distance is 0. The maximal distance will be mapped to 65535, which is the maximal number for the unsigned short integers. The return distance should be scaled back to the floating point numbers. So for the permutation vector 0, 4, 2, 3, 1, we can generate the distance by looking up the 0 row, and then we get this instance. And then for 4 to 2, we get this number. From 2 to 3, we get this number. And the last, we get from 3 to 1, we get this number. The sum of these four numbers are 7262, and then we convert that to the floating numbers. We can find there's a little error between the sum of these floating point numbers and the converted back numbers, but a little error is acceptable. Then we run a simple CPU implementation. This implementation is written purely in C language and compiled by G++. Then we run a simple CPU implementation. This implementation is written purely in C code and C language, and then we compile with G++ compiler. We run this program on all HLS server, and then we can see it takes a quarter of a second to run for n is equal to 11, and 2 seconds, and then for 41 seconds. We can see the problem size scales when the n increases. Because this lab is originally made for VTIS HLS, we want to map this lab from the VTIS HLS to VTIS IDE. So we rewrite the entire kernel function. The first EL has mentioned that the naming mangling issues, because the V++ compiler created by VTIS is to run a link operation after it finishes compilation. If in C++, the name of the function are usually mangled, so the linker cannot recognize the mangled name of the function. So we should wrap the top function, only the top function, by extend C. The function's code is not needed to wrap by extend C. And the second, because we would like to use the OpenCL for host program, so we replace the SLS string with a pointer. The first, for the original program, it used the standard library here. We eliminate this template for this name mangling issues. And then the host program are also rewrite. I borrow this program from our lab 3, so the entire program is not attached in this lab. So for the we should allocate two pieces of memories. One for the input distance, which is the lookup table with n square of size. And then we should allocate the memory for output distance, which is only one scalar of unsigned integer. And then we should, before we start the kernel, we should copy input data, which is n square lookup table to the global memory. So we can see, because there's only one kernel here, unlike the lab 3, we have 5 kernels in lab 3. So there's no kernel event dependency. We only depend on the previous memory copy event. So we should simply evoke this kernel execution. After the kernel execution, we should copy the result back, which is simple and similar to lab 3. This is all software emulation result here. We can see the result here. 75662 computed is the same as we explained before. And its execution time is only 3 milliseconds by emulation. And for n is equal to 11, it gives about 1 second, which is much larger than the CPU execution time. But for the actual hardware execution, it only gives about 400 milliseconds, but it's still slower than CPU. What's wrong here? Because in the original version, I do not use the storage binding. Because I directly to access this lookup table on the global memory of the device. So it will be very slow because the distance between the logic and the global memory. So a pragma binds storage is added to instruct the compiler to use a RAM with 1 write port and n read port using n banks internally to create a memory, and then we use preflux and lookup tables as a memory. It doesn't even use the block RAM. We have 11 square words. Each word has 16 bits. And after the story binding, we can see the duration, the execution time of the kernel is reduced and become much faster, which is outperformed by CPU implementation. And then we seek the room for further performance acceleration. We can create a 4 parallel design by copy the 4 copies of the distance table. So we have 4 pieces of memory on the created as RAM, and then we create 4 kernels, create 4 instances of the computation to parallelly execute partial result of the I, and then compare among the 4 candidates generated by the 4 independent subfunctions. And then we can see for the 4 parallel design, the memory used is scroll, and then the DSP is also growth. For the 4 parallel design, the memory is used can be seen as here. So for the 4 parallel design is 3.84 faster than the fully serial design, which is nearly 4, but there's some overhead by the copy generated by the copy subroutine, so it cannot achieve to 4, but it's much faster than the CPU implementation. Thank you for listening.
Can you go back to the code? Yeah. Yeah. So my question is, right now, kind of manually partition the distance. You have a whole distance.
Yes. Which is the same.
You create the distance table for input.
And then
You call the function.
so now
Actually, each one only work on part of the table.
part of the permutation.
So you have the distance table, you have a full copy of the distance table.
Yes.
And you have a full kernel function. And then,
And here, compute.
so my question is the distance table. You have a full copy of the distance table.
Yes.
In the PTA.
To avoid congestion.
So actually, the compute is only each of the compute is only work on part of the
All of the distance table.
work on the whole distance table.
Whole distance table. Yes. On each copy.
Each one work on the whole distance table.
With a different I. I is the index of the permutation.
Oh, okay. So actually, it's a part of the distance table. It doesn't work on the whole distance.
Part of the permutation.
The whole distance table, part of the permutation.
Yes. Part of the permutation. For the distance table.
So you have to save your whole table. Either at PTA, my question is, either at PTA, you have a whole distance.
Yes.
It may not be a PTA.
No. They are created in FF and LT and lookup table.
Yeah. So the distance table will save in the distributed.
The hardware overhead is little, very little.
Yeah. However, yeah. But I mean the distance table. How many copies of the distance table?
4 copies.
4 copies. So
There are another 6 presentations, so we will do that on Wednesday, 7, start at 7, right? Okay, so today, yeah, let's call it a day. Yeah, okay, thank you.